Howdy, everybody. Hope your day, night, morning, whatever, whenever you are, is treating you well. We're here for day 13 of Advent of Code. This one was an interesting one. Um, it actually turned out to be really easy to solve. Although at first, like at first glance, it seemed like it would be one that I'd have to like pull out my dynamic programming chops, try and remember some of that stuff. We'll talk about that in a second. If you can see my tabs up here, you kind of see where we go with some of this stuff. Oh, do I have my other thing up? Yeah, I do. Okay. Uh, anyway, it's called claw contraption, and the gist of it is you're at a resort and you find a bunch of arcade. You find an arcade there that has a bunch of claw machines, and the way that you use the claw machines is you press two buttons, and one button moves it moves the claw some number of places, like up and to the right, and then another one moves it a different number of places up and to the right. And the question is like, can you use those two buttons to like get you to the prize? So here's the example input they give you. They say, okay, button A increments x by 94 and y by 34. Button B increments x by 22 and y by 67. And so using those two buttons, can you get to the prize that's located at 8,400 and 5,400? Not only that, but it says like, what's the smallest number that you'd have to do? What's the smallest number you could use to get there? And it also says later, like each, like pressing the A button, or I guess it says it earlier. It costs 3 tokens to push the A button and 1 token to push the B button. So what it's saying is like, what's the minimum number of tokens you can use to get to the prize, if you can get to the prize? Like it says, I think down here, the second and fourth claw machines, there's no combination of A and B that will ever get you to a prize. So like this one doesn't actually work, and this one doesn't. You could like never actually get here using these two values. Um, so the when you read, or at least the way that I first read it, the way that it came to my mind was, oh, this is like a minimization problem. There's going to be, you know, if I press A 50 times and B 40 times, does that get me there? Maybe it does, or it doesn't. Well, it doesn't in this case. I know it doesn't, but if that gets me there, and then I can press A 10 times and B 60 times, and that gets me there. Which of those is cheaper? And then pick that one, right? If that makes sense. And this is used in dynamic programming. I actually almost want to open up another whiteboard. I think we've done dynamic programming problems before, but these minimization problems, I at least find them kind of fun because they take me a little while to think through. But if you imagine like a table like this, please excuse my drawings, and you're trying to the prize is right here, and you start right here. You can imagine like pushing the buttons like moves you through this table and gets you to the prize right here, right? Eventually you get to the prize. And the way that these dynamic programming ones work with tables is you can kind of figure it out. You could say like the way that it works with dynamic programming, I should say, is instead of like trying to solve the whole problem, why don't you just solve like the nearest problems to get you to the prize and then work your way out? So maybe you say, oh, to go from here to here, it's like the total cost is 3, and to go from here it's 1. And then when you ask this question, like what is the cheapest to go from here to here, you then add that to this value. And so maybe the cost to go from here to here is 2, so that makes it 5. But to go from here to here, the cheapest is 2, and that's cheaper than 5. So you know the cheapest way to get from this point to this point is now 2, right? And the way you'd go is this way. I should mention that you can solve this with like graphing algorithms as well. If you think about the problem that they're asking, you can ask this same question with or you can answer this question with a graph, in that you can say like, okay, well, I'm going to use like Dijkstra's algorithm or something like that, and slowly move either the A or the B direction, and then track the total cost, and like try and find the minimum cost to get there. So the way this graphing algorithm would work, the neighbors would be like incrementing A or incrementing B, and then the additional cost of incrementing A or B, and then Dijkstra would find the fastest way to get you there, right? But this dynamic programming also works, right? Is the idea is, once you've figured out this one, you can then, and you slowly fill out this table, right? And so as you're filling out this table, you just ask yourself, okay, well, if I'm here, how much does it cost me to go from here to here and here to here? And then pick the lowest one. And eventually you make your way up, and let's say the number is 75. Now you've found like the shortest way to get up there. And I apologize if I didn't do dynamic programming justice. I'm sure I've done videos on it. If I haven't, there's lots of ways to like, I may not be able to get my leak code stuff. I think I tried to look for one in here. Let me just see if I can. My lists. I don't know what this is. Submissions. Oh, here we go. Oh, okay. This is probably one. Maximum value of K coins from piles. Let's see if I can get to my submission. So I don't know if I actually did a video solving this one, but if you look at like what the problem is, it turns out like this one's a maximization problem, but you could also do it with minimization. The just difference is, are you maximizing or minimizing? You can see here I keep like a DP, which is a dynamic programming array, and then I just like minimize and maximize the values in my for loop. And that's essentially, so again, sorry for this tangent. This is potentially a way that you could solve this problem, at least for part one. If you when we get to part two, you'll see there's like actually no way to solve it like this for part two, just because the space of the problem is so large. That being said, when I was reading the problem and thinking about this, I did initially think like, oh, is this dynamic programming and how do I solve it this way? But after analyzing the problem a little bit, sorry, let me get back to my thing. After looking at this a little bit, it occurred to me that this is really just because the values are, you only have like 2 buttons you can press, and you only have like the X and Y values for each of the buttons in the prize. This is actually just a system of linear equations, right? So you can imagine, maybe I can find it somewhere in here. Yeah, right here. I use A and B here because because the values are X and Y. So you'll see in a minute. But if you think about it, like this value, the 2 systems of equations you're trying to solve are, what value can I put here and multiply by 94 and add that to some other value that I multiply by 22 that gets me to 8,400. And then you do the same thing with this equation over here. That is to say, there's some value. There is some value A and B such that, sorry, I had to write that out, such that this applies, right? So 94 times A plus 22 times B equals 8,400, and 34A times 67B equals 5,400. Like, that's the notion, right? And so this is, you're actually seeing what I drew out as I was trying to do it. You probably saw this in like junior high or maybe high school. I guess I don't know when everyone does algebra, but like, so this is something, solving a linear system of linear equations. This is something you'd done in like an algebra class, right? Is where you say, okay, how do I solve this? And obviously you can use linear algebra, which we'll talk about in a little bit later, but you can actually just use high school math with it, right? Or whatever, the algebra with it. So you can see that's kind of what I did here, right? Is like the way you solve these equations is like you can say, I mean, you could do some stuff where you say, oh, I'm going to, half all of them and stuff like that. But you can also just say, hey, solve for A in one of them and then plug that value in the other to help you solve for B, which is what I did over here, right? So I solve for A. Notice I'm not doing the math right here. I'm like leaving it. And that's because in the problem, it talks about it being an exact solution. There are exact solutions and no solutions. And the reason why that would be, right, is like you can't press a button 0.3 times or 0.2 times or whatever. Like you either press a button or you don't press a button. And what's that's telling you is like at the end, all of the math should come out to like a very specific number, an integer, if it worked, right? Like if this was 35.7631, that would be the solution to this equation, but it wouldn't be a solution to the problem because you can't press the button 35.7631 times, right? So that's why I kind of left it out here until I got to the end and you see me doing some weird algebra. But like basically I solve for A and then I put that in A in place of A for the second equation, and then I do some work, right? I think I multiply the whole thing by 34 to get rid of the denominators here. And then I can just do the math across these numbers, and the answer for B turns out to be 40. And then I can plug 40 into the other equation now that I know what B is, and that will give me the value of A, which is 80, right? So this is all just, again, doing math, solving systems of linear equations. And as you can see, like for part 1, that gives me the right answer, right? You press A 80 times, B 40 times, and that's why I use A and B, because it's the buttons A and B. Anyway, you press A 40 times, B A 80, B 40, and that gets you to the position. And then you add up the cost of the tokens, right? Pressing A 80 times costs 3 each one, gives you a total, and then add that to 40, that gives you a total of 280. So that's it. It's like you say to yourself, I don't even have to do dynamic programming. That's literally I just do some algebra and get to the solution. So what does that look like? Well, obviously there's hundreds of these. I guess I don't know how many there are. There's a sufficient number of them that I don't want to do them all by hand. That being said, this is a potentially one that you could do by hand. I've seen days where people have said, oh, I just did it by hand. And this is definitely one where you could potentially do that. So what did I do? Is I just tried to come up with a generic solution to this. And I probably should have just looked on the internet, because I guess I reinvented the wheel, is to say this. So I just made the values, like instead of saying 94 and 22, I just said, oh, I'm going to make some variables for those. So I have x1a plus x2b equals x3, y1a plus y2b equals y3. And then I do the same thing. And so the code here looks substantially crazier because I'm using variables instead of actual numbers. But you can see I get to this value right here, where b is equal to y1 x3 minus x1 y3 all over y1 x2 minus x1 y2, and then a is equal to x3 minus x2b, right? So I solve for b first, and then I plug b into there, and I can just do a is equal to x3 minus x2b over x1. And that gets me to my solution, right? So now I can just say, okay, if I know what these values are, I can literally just do the math and solve for B, solve for A, and then multiply the things together. So that's actually what my code does. So this is the intuition and me doing like the pre-work, and then I can go to my code and like literally show you how I solve it, right? So what does that look like? Of course, I make a point because we're moving in a point in space. And I thought at the time I'd definitely be doing dynamic programming. I think having the point still helps, and I'll show you why in a minute. Anyway, I used nom to parse this. You can see over here that you kind of want to just get to the 94 and 34 and the 22 and 67 and then the 8400 and 5400. Nom felt really good for that, so I just did that. You could probably use something like split by space, trim the x plus and the y plus, and bully, you got there. But I use nom, and so you can see here's how you parse one of these buttons. You strip off the A and the B, and then you strip off all of this part right here, and then you get the digit, and that's your x value. Then you strip out the comma y plus, and you get that y value, and then you pull out the new line so that you can parse each of them. And then the prize is the same thing, right? You still want an x and y value. You just want it just looks different, right? So you parse the x equals, get the x value, parse out the y equals, get the y value, and pull out the new lines. Notably, I do an opt here when I'm doing my nom parsing, and that's because if I don't do an opt and say it has to end in a new line, if this last one doesn't end in a new line, it won't be included. I ran into that bug as I was testing nom. The idea is like, if you say there should be a new line at the end of it and nom doesn't find it, it won't consider this line to be a prize, which won't make this a whole, like a machine, and then you won't get the last one. So I say, hey, optionally strip off the RN at the end right here, but if there isn't one, that's okay. We can still get the prize without that at the end. Let's see. I implement add just to do some simple addition somewhere. But then to create the machine, I just do a parse of, get me the A button, get me the B button, get me the prize, and then I return that machine. Okay. And so you can see what I do is, here's part one, is I basically just, once I've parsed all the machines, I can just iterate through all of them and call solve on them and sum them up. Notably, I'm doing a filter map here, and that's because solve could potentially return none, right? If you remember back at the problem, these 4 test cases, 2 of them don't have a solution. So you have to figure that into your thing, and that took me, it did take a lot of time, but it was something that I had to be careful of, and I'll show you why that is in a second. Because you could potentially just say, now I know what B is, I just do this math, and A is I just do this math, and I return that value. But you're going to run into a problem if this part right here equals 0, right? You can't divide by 0. That doesn't work. You also get that problem over here if x1 equals 0, right? So that's bad. No bueno. So you got to check for that case, right? And then you also just have to check of, like, when you do this division, does it divide by a whole number? Like, is there a decimal after it? And so that's essentially what I do. So let's look at my solve to show you what all that looks like. You can see here, because I use x1, y1, x2, y2, x3, y3, I went and just set those values here. So I could like easily transition from my whiteboard to code. And then I just get the numerator for B and the denominator for B, and then I do some checks, right? I say, if the denominator is 0, there's no solution. In linear algebra, I think this is like the infinite solution problem. Like there's, what is it? AX equals B or something like that. If the determinant is 0, I guess I don't remember. I'm mixing up my linear algebra stuff, so please ignore that last 10 seconds. But the idea is can't divide by 0. And then also, if it doesn't divide evenly, meaning I have no remainder after I do a modulus, that's also not a solution either, so I return none. Otherwise, I know there's an exact solution, and so I can solve for B, and then I just do the same thing for A. And so you can see here, I've literally just pulled what was right here, done this and this and this and this, and I've literally just put that stuff here and here and here and here, and then just done the operations to give me some A and B. And you can see when I run it, it returns essentially instantly because I'm just doing math, and I'm just doing math like 100 times. So I don't have to do dynamic programming to try and solve it. And that becomes important in part 2. So let's look at what part 2 says really quick. Once you do all this math and you solve the problem, it says, oh, there's a mistake. There's a unit conversion error. And actually the prize is, what is this number? 100,000 million, a billion, 10 trillion higher than before. So instead of it being 8,400, it's now 10 trillion 80 and 8,400 higher. That's where the prize is, right? So basically you add that 10 trillion to X and Y, and now you're trying to solve this number. And that's where solving it like this becomes a nightmare, right? Because now your state space of like trying to solve this is like really huge. I didn't actually look. It might be interesting. There may be some math to this 10 trillion number where you where you can simplify. Like there may be some relationship between these two values that allows you to simplify this. But that I didn't go down any of this path. I didn't even try it because I had already solved it with part 1 and using like math. So my solution is 01, right? I can just do some math and solve it. And so I just have to add this huge number, 10 trillion, which I hope it is now that I've said it a bunch of times, to the problem to solve it. So my part 2, the only thing that changes is before I solve the prize, before I call solve, like I do up here, I just add the conversion error to my prize, and then I call solve, and I get the solution for part 2. And you can see it runs like just as fast. I just get some ginormous number as opposed to the normal smaller number for part 1. So part 2, if you did it that way in part 1, if you used math in part 1, it turns out that that's part 2 is a simple no-brainer. You have no issue with it. You could have probably estimated that something would blow up. I don't know. When I first read it, I was thinking dynamic programming, and so you ask yourself is like, oh, is the problem like you can brute force part 1 and then you have to do dynamic programming for part 2, something along those lines. And so that's why my mind was leading to dynamic programming, but this one was actually the opposite way, right? And so I don't know if you could. I mean, maybe you guessed and had some intuition and said, oh, these numbers are going to blow up and dynamic programming isn't going to work. Is there a math solution to it? And so if you did it that way, that would help. I just happened upon the math solution because I was like, reviewing the problem, and I was like, oh, this is really just a math problem, right? I've done this before 1,000 times. And so you all had to do like, when you were in algebra, your teacher would give you homework and it was like 60 problems every day. Anyway, I've solved these systems of linear equations a lot. And they actually are related to linear algebra, which is what I would like to kind of like talk about next. After I solved it, I was going around and looking, is there a linear algebra way to do this? Because you can actually just describe this as, where's my thing? This can actually be described as, I'll move over here to the side, like x1, x2, y1, y2, a, b is equal to x3, y3. And I'm using my x and y values right here, but like this is the linear equation you're actually trying to solve in like linear algebra, right? This is what you're trying to solve, and it turns out this is already well known, and and it's based on this thing, Kramer's rule, which I don't think I've heard about before. The one that I was thinking about was like, how do you solve these linear equations in like a general form? And it was actually Gaussian elimination. Yeah, this part right here. In the case of n plus one determinants, one Gaussian single determinant. Anyway, we'll talk. I'll show you that in a second. But the idea is, let me find this place right here. If you have this system of linear equations, which is exactly what we have, and I apologize, it's confusing here because they're using A1, B1, and C1 to solve for X and Y. But this is exactly what we're solving for in the problem. It turns out that you can that this translates into these two values. X is this, and Y is this. Or in our case, for our problem, pressing the A button is this, and pressing the B button is this. And you'll look, even again, I apologize, these variables look odd, but they're exactly the same as, it's not in my code, they're exactly the same as, I'll get there, this right here, right? It's exactly the same as this, it's just the variables are different. And so I suppose I could have just Googled and found the answer faster. But I got there just because I was like, oh, I know how to do this. Anyway, this is, I don't, what Kramer's rule, what it's actually used for is to say, Kramer's rule is like a proof that says if you have a system of linear equations and with as many equations as unknowns, there has to be when it's valid, then it has a unique solution. Sorry, it's taking me a minute to say that correctly. Essentially, what Kramer's rule says is like, because we only have an X and a Y, and we have two solutions, or we have two equations, we should always be able to solve for X and Y. So the only thing you have to do is ensure that that denominator isn't zero, and then for this specific case, that it turns into a whole number, right? So those are the things that you have to check for. I believe Kramer's rule talks about dividing by zero somewhere. Assume A1 B2 minus B1 A2 is non-zero, then with the help of determinants, X and Y can be found as this, right? So this can't be zero because it's the denominator of these values. And that's what they're saying is, it can't be zero because that would be, I think what it means is an infinite number of solutions. Or maybe zero solutions. I think what it means is there's zero solutions. Anyway, I don't remember which of those are. I should take my linear algebra course again, which is, I actually looked it up. Here it is. Do you guys use Udemy? Not a sponsor. I have this course on linear algebra, and I've used it before to like remind myself of stuff that I've done in the past, right? Way back, and that I've long since forgotten. And I think this is the one. Is this where it talks about Gaussian elimination? No. Oh, this is just talking about the number of solutions. Yes, so here is a unique solution. There's infinite or no solutions for this one, and that's because this bottom row is zero. Yeah, so I think that's what this means. If this is zero, it means there's infinite or none. Maybe it's both. Anyway, shout out. If you want to learn linear algebra, I actually enjoyed this course, so feel free to look it up. It's called Become a Linear Algebra Master. They give you practice problems that you can work on, and I think she does a really good job of it. So feel free. If you haven't done linear algebra before and this Kramer rule or all this stuff doesn't make sense to you, it was a fun course for me to learn like the very basics of linear algebra. And I still, like I said, I still refer to it. I went back and like operations on somewhere in here. Gauss Jordan elimination. This is the one where I was all like, oh, I wonder if I could use Gauss Jordan elimination because we have a system of linear equations. And so you can follow like a set of rules to get yourself to a thing, right? And so you could potentially create an actual algorithm to solve it this way, I guess is what I'm saying. In our case, we didn't because we could use this Kramer's rule to come up with like a very exact solution to our single problem, which makes our solution like, super easy to solve. So again, just a real highlight of like, or to review what happens or what happened to me. It felt like it might be a dynamic programming problem, but when I'm like analyzing it and looking at the problem, it became clear that like, oh, I can kind of just ignore that dynamic programming. And this is just two systems. It's a system of linear equations with two equations in it and two variables. I know how to solve that with math. Can I come up with a generic way of doing that? And I re-implemented this Kramer's rule somehow to get to this value right here. And then this makes it super easy to solve, right? The one gotcha again is this exactly, right? So just make sure that if you're doing this yourself, or maybe you stumbled upon it and had some issues, this exactly thing makes it clear that like if you're getting to some non-integer value in your math, or you're dividing by 0, that's the sign that maybe something's gone wrong here. And then there is no solution like this one. I didn't check why this one has no solution. But it might be like the divide by 0. Or it could be just that like the dividing gets you some decimal value. And if it gets you a decimal value, then that can't be it. Anyway, so that was the problem. I wanted to go look again. I would be interested in how you solved it, first of all. So what did you do to solve this problem? If you did the math way, that's cool. I'd like to see it. Maybe you have some other way. Did you like the Gaussian elimination? Is that it? Or the Gauss-Jordan elimination thing? I don't think this is the same. Mine was a Gauss-Jordan. Oh, it is Gaussian elimination. Gauss-Jordan elimination. This is a cool way. I don't think I've ever tried to write an algorithm to do this. I have used like NumPy's solver for like 2 matrices or solver 4 matrices to do this work before. So that's a cool way. But I just wanted to go look at other solutions and talk to it. So I brought up Reddit, and I thought we'll just spend the next few minutes seeing what everyone's happening here. So should I refresh it, get the latest, get the freshest? Everything to get that prize. Me after spending nearly 100 trillions on the claw machine. I'm once again asking for your financial support. Okay. Yeah, you do have to click those A and B buttons a lot, right? To get there. Get out of how math. I just want to do AOC. Luke, I am AOC. No. Yeah. That I guess I didn't say this before. There are some days in previous years where it was a math problem. And if you knew the math, you solved it easy. If you didn't, you could do some brute force on part 1, but probably not on part 2. I don't remember the days specifically, but there's there's always a couple days where it's just math, and that helps you. You could not live with your own failure. Yeah, okay, BFS, DFS. So like this again, this is a part 1. You could definitely, I think you could definitely solve with dynamic programming. The sizes are small enough that you probably could. What is this? The inverse matrix? Did he just copy an image of linear algebra? Basically. But yeah, linear algebra. I mean, technically what I did was not linear algebra. I just used straight up algebra. But you could use like Gaussian elimination again to solve it, or Gauss-Jordan. I don't know. Maybe it's both. Yeah. Yeah, if you solve part 1 with recursion using like DP or whatever, not good. It is a funny thing is like how long would it take you to press all those buttons to get to the prize? Is it really worth that many tokens? What is the prize that we're doing? Just add the numbers? Oh no. Yeah, this one was a one where it's like it was math, I presume. We'll look at some solutions, maybe. Ooh, okay. So if you're using Python and you use like the SciPy or the NumPy libraries, it will hold fractions for you and give you whole numbers or fractions. And then it never, I don't know how it does it, but under the hood, it never actually converts it to a float. So you get something like this. Um, And so, like, I've done in my linear algebra courses, like when I check my answers, I'll go to Python and like do it, and it will return the fraction for me, right? So I can make sure that I've got the fraction correct. So this could be a thing that you run into, excuse me, in like Python or especially JavaScript, where every number is a float. You could run into this problem, right? So there you go. Anyway, that's just a little tip is you can use some libraries that treat it as a fraction, and so you get a fraction back and you don't have to worry about this kind of thing right here, because the fraction will become a whole number if it comes out okay. Oh boy, only 2 bajillion more presses to go. I have seen streamers that have this little thing on there that's clacking for them. Yeah, it's absurd. You're pressing those buttons. When I went to school for this, I didn't have a computer. Yeah. I mean, they had computers when I was in junior high. We used to play games like Commander Keen. Shout out in the comments if you ever played Commander Keen on your computer in school. Yeah, this is a good one for pen and paper. I don't think you can solve. I mean, it's good to go to pen and paper to like get to this, but like, do you really want to solve every single one of these with pen and paper? I don't know if you do. I didn't even look how many there are. Should we just look really quick? Um, oh no, I don't. 320. So do you want to solve 320 math problems? Probably not. I need to go back to grade school. Hey, you know what? It helps to have children because it reminded it like yesterday. It reminded me of the sides and corners, helping them with all their math homework and stuff like that. Actually, like I feel like it keeps me up to date on my stuff. Right? I don't just brain rot it away. Day 13. Okay, I think he's probably just going over what I explained largely, right? Like there's some X value that gets you to here, and there's some Y value that gets you to here, and you're just solving those two problems. Kramer's rule gets you this, and so you just do the math. What is this right here? Is this like a Python thing where you can divide by do integer division or something like that? Or maybe it's just like he thinks he's in latex or something. I don't know. Let's see here. Oh, this is an interesting way. Does he check? Yeah, he doesn't check if the determinant is divisible by 0 or is 0. Maybe there's no cases in the problem where the determinant is 0. So you don't actually have to check. Like that's in a generalized case, you definitely have to check that the determinant is 0 or is not 0, I should say. You definitely have to check that it's not 0. But cuz this would fail right here, right? But this is an interesting way to check if it's a whole number. So in my code, I checked if it excuse me, if the modulo divide, so the modulo operator, so divide with get the remainder of a division was 0. In this case, he's saying if I multiply these two numbers together, do I get the exact prize value? Because like if A and B came out to be like some fraction, it would have like rounded down and like say it's 39.58, this would have been 39, and then this would not have gotten you to the prize. So he's basically he's like checking his work to see if that gets you to the X and Y value you're expecting for the prize. So that's a good way to do that. I don't know if it's faster or slower than just checking the modulo operator, because you're still doing multiplication here. It's probably not faster or slower. It's just a different way, but that totally works. Yeah, this is the collinear thing, right? If there would be no solutions, but I think we determined. I mean, if his function works, then there clearly none of them were collinear. Like where the way it wouldn't have, it would have been that like there's infinite or no solutions. If like you could test for that too to see if they're collinear. Like imagine if where can I show this? Imagine if it was the values were something like 2 and 4 and 8 and 16. These are like collinear, and you wouldn't have been able to solve it, right? So I think that's what he's saying. Is that what collinear means? Yeah, I think so. Like it turns out that these two, I mean, these both are 1 comma 2, just scaled, right? And so what it means is you actually don't have a system of linear, what it means is you don't have a system of linear equations like right here. You actually only have one equation, and you cannot solve two unknowns with one equation, if that makes sense. Like that's what we're looking for. Or that's the case you'd have to check. I don't think I checked that in my case either. Oh, I do, because I would have gotten 0 for the no. The determinant is different. How to test? I have to look this up. How to test if collinear. I spelled that wrong, huh? Algebra. Isn't it something like 1 over? Oh, it is the determinant is 0. So his problem does test it. Oh no, he doesn't. That's what I was pointing out earlier. He doesn't test if the determinant is 0, which you do have to do, right? So mine does actually check if it's collinear. His does not. Okay, it took me a minute to get there, but I got there. I do check for collinearity, right? Like I say, if the denominator is 0, then I return none because they're collinear. There can't be a solution. Day 12, we talked about that. Day 13. Some of these are cool, right? You're doing your programming on a Nintendo Switch. I mean, I have a Switch over here. Should I try and do? I actually don't know how you do that. Anyway, very cool. Wait, coding is just linear algebra, always has been. Yeah. Especially today, if you a lot of data science and computer stuff, spend a lot of time in linear algebra, right? I even like I work in an industry totally unrelated to what you would think is math, but we use a lot of linear algebra, so we're all chilling, but someone's losing real money here. The nerd did maths in high. Okay, that's awesome. That's a pretty good one. That's pretty funny. Oh, it's today Friday. It is Friday the 13th. Matrix inversion. I actually. Yeah, you could definitely solve it with linear algebra, right? I mean, I don't know why. I mean, technically, this. I did not solve it with linear algebra. I don't know. Maybe I did because I got here. I used Kramer's rule, so maybe technically it was linear algebra. I wouldn't consider it. Okay, let's look at some actual solutions, and then we'll be done instead of the memeing. What the C plus plus? What has C plus plus become? I mean, this. I didn't realize how functional C plus plus could be. Okay, I mean, it looks like you're just doing the math, right? Here's the determinant right here. Solve the equations by hand. Rage. Yeah, it's okay. There you go. This is the thing is like so I that this getting from here to here like often feels just as good as like oh I can solve this using some arcane algorithm that's really fun. Okay, but it was math. That's very cool. Let's look at some Rust solutions. Somehow my tests in part one were passing, but part two is wrong. Stole someone else's solution. Okay. Again, I think we talked about that yesterday. There's nothing wrong with that. Oh, that's cool. He's splitting on these, and then he can just take the exact ones that he needs. Interesting. Okay, but it's just linear algebra. I mean, again, he's just doing the math, right? It's just solving. Why does this work on part one but not part two? I-32? I kind of want to run his code and know why it doesn't work. I mean, it's definitely not using. Oh, that is not the determinant, right? I kind of glossed over it, but it's not. It's not subtracting. Oh, he's just trying it 100 times. Oh, that's interesting because there is a somewhere in here it says you estimate that each button would need to be pressed no more than 100 times to win a prize. So you can actually stop at 100. Okay, so what he's actually doing is like he's just saying for A and B, see how if I press, he's literally brute forcing it. If I press A this many times and B this many times, does that get me to what I want? If so, I return the solution. So why wouldn't this work in part two? Is because I mean, what does he mean? It didn't give you the right answer. You have to do it like, what does he say? Stolen, but part two is wrong. I don't know what he means by part two is wrong. I don't think you'd actually do it this way because what changes in part two is it says it'll take many more than 100 presses to do so. Uh, like what it's saying is you can't have that like limit anymore. You just have to keep going until you get there. So now instead of testing like A 100 times and B 100 times, you have to like test all over the place. Maybe that's what he meant by he couldn't get it, so he just reverted to math. And it's okay if you don't know the math, right? I mean, I tend to like math. Like I said, is it Math Nerd that I buy these things on Udemy and watch them for fun? Probably. There's some high school jock that's gonna give me a swirly, I'm sure. Just break into my room and do it right now. Okay. I'm really curious if anyone did. Then invert to find the answer. Each claw machine is a system of linear equations, shortening the names and representing its matrices. Check for determinant. Integer solutions only. Yeah, there you go. Okay, he did the same check as me. Sometimes people say things that I don't understand. Invert it to find the answer? What does that mean? I mean, I know about inverting a matrix. Is that what you're doing? Maybe someone who's smarter can tell me. Or I should just go back and talk. Because, like, where? Surely somewhere in here it talks about matrix inversions. Matrix inversions, solving systems with inverse matrices.
Now that we know about inverse matrices and how to find them, we want to recognize
we know already how to solve using substitution, elimination, and graphing. This time we want to talk about how to solve the system using inverse matrices. Okay, so you can do it this way, but I presume it just gets you to Kramer's rule. So that's what it's talking. That's that. I mean, the what he's saying here makes sense from, I guess, from a linear algebra perspective. I just wasn't paying attention close enough. Let's look for DP. Dynamic. I really want to find someone who solved it dynamically. Bummer. Oh, here's in Go brute force. This does not look like it. Looks like it literally is brute force. Oh, here's another trick. I don't remember if I mentioned this earlier in the day, but it said that there could be more than one solution, or what's the fewest possible, which is why it leads you down the dynamic programming path. But if you actually think about the problem, there either is a solution to this or there isn't, right? Like, um, yeah, I'm pretty sure that's the case. There either is a solution or there isn't. There is either exactly one or there are no solutions, right? Isn't that what kind of like Kramer rules says? It has a unique solution. So like, because we have two variables and two equations, it either does not work or it works exactly for one set of values, right? These values right here, it's either not a number or no solution, or x is this and y is this, and there's no like multiple ways to solve this. So let's keep going, see if I can find one. I really would like to see someone's DP solution. What is this regex parser? Yeah, again, I use nom, but you could probably use just like a simple parser and maybe look at like this. Uh, Here's the determinant. No, right here. Here's the determinant. Here's the top. Okay, so he just used math. Oh. Oh no, he does it the same way. I was trying to think, is he just like slowly? No, he's not. Okay, yeah, I had misread this. He like first checks, is it equally dividable, and if it is, then you can add that to your solution. And then he just does the multiply by 3 and the add at the end, right? So he's tracking the A totals and the B totals, and eventually you get there. Okay, so it is just math. I don't know why he says solution. Maybe it's just, oh, he does say 100 microseconds. So that's fast. For some reason, I think he's saying 100 milliseconds. So I'm like, that is a little slow for doing math. So I just misread. Very good solution. Yeah, we came up there. I had to dig deep to remember Kramer's rule. Okay, everyone's using math. If you solved it in dynamic programming, I would love to see how you solve part 1 in dynamic programming. I know you can't do part 2, but I want to see part 1 in dynamic programming just because I never tried. I didn't try it at all. I got to the math before I actually started coding. Um, oh, Z3. We've used Z3 before in our problems, right? Very cool. Very cool. So if you don't know what Z3 is, it's like a very cool solver. You give it some constraints and some values, and you say like, I want to get to this solution, and then it does like some complex stuff to get there, and it's not brute force, right? It's slower than like traditional linear algebra, especially for this problem, because it has to do some like it's doing some mathing to like kind of hone in on a correct answer, which is really cool. But yeah, you don't have to do this for this part. But that is cool that he used Z3. So that's another way that you could have solved this problem, is if you'd known about Z3. You could put the stuff in there and say, oh, I here's my two equations, here's the values, uh, or the assertions I have to make right here that he does, and then find minimize the value, minimize that solution, and then if it gives you a result, you can return it. Right? Very cool. Very cool. Very cool. Where did we use Z3 previously? Oh, I think it had to do with like throwing a rock to hit icicles or something like that, right? Very cool. So Z3 is another solution for both parts. That I like that one. Very cool. Yeah. You can do this in really. My code is always very bloated because I like to do comments and variable names and stuff like that, and I like to create data structures like the point. Have I used a point like in every single day this year? Maybe. And so I like to build data structures so my solutions are relatively long. But you could definitely, if you're going for a minimalist thing, like solve it like this. There you go. Yeah, and you just filter. Okay, he filter maps to get the what is this? Oh, that's cool. So he's splitting and then getting the integers, and then he turns the each three lines into a tuple of 6, and then he can solve that tuple of 6. Okay, very cool. Yeah, so you can get this really small. Very cool. I like that. It's definitely not like, can you imagine? And I've had, especially in the early ones when I just do the live solves, my code looks pretty bad. And like, it's kind of hard to grok and read, right? So I do spend a lot of time on these days when I'm just doing a solution is like, how can I clean up my code a little bit to make it more readable? And that's where you get like, things like this and comments and stuff like that. But these are very cool. I really like this one. That's very cool. Man, I can't find one. I'm going to stop looking. We'll just end it right here. Overall, a very cool day. Um, if you have a math background, a linear algebra background, I think you could have easily gotten there. Again, it did try and trick me with dynamic programming at first. But this is always something to look out for. I think he does this on purpose sometimes, is kind of like make the solution feel like it's going one way, but it actually ends up like taking a hard turn on part 2. So you have to go a completely different direction, right? Like I think that's happened before where it's like, oh, I can just brute force part 1, and then part 2 is like, well, I can't brute force it, right? Or in this case, it was, can I do dynamic programming for part 1? Well, I can't do dynamic programming on that number, right? So anyway, very cool day. If you're not a math fan, you probably didn't like this day because it's just a bunch of mathematics. But it's puzzle solving, right? So solve it the way you can solve it. And he always throws in a couple of math days. I'm sure there'll be another one, right? There's always math days. And even if there's not math days, people spend a lot of time making non-math days math days. And they have just as fun doing that, right? So if you like math, try and solve it with math. If you don't, try and solve it another way. I would be very interested if you can solve this some other way other than math. If I had gotten to this point, I would just be like, oh, there's no way. Well, I mean, you can use the Z3 solver. That works too, right? So that would have helped. Anyway, very fun day. I hope you had fun too. Send me your solutions. I'd like to see them. Uh, uh, Especially if you got your one-liners still out there. Love to see them. You could potentially do this one in one line, right? We saw that previous solution where like it would be a very long, like, quote unquote one-liner but you're basically just doing math on values. So this one's definitely a one-liner one. I'd love to see your one-liners if you got them, but send me your solutions. I really like to see them. They're always fun. So we'll talk to you tomorrow for the next day.